so let's start. Unfortunately, today no one has joined, so I think everyone is celebrating Independence Day, but that's fine. Basically, everyone should celebrate Independence Day. It's a national holiday, so everyone wants to leave. But since this is like weekly tutorial sessions, this cannot go. We cannot have a leave, so I will be conducting the session. So if anyone wants to look at the session, they can just simply go through the video that I will be uploading on my YouTube channel, and I will also be uploading the sharing the slides. So if anyone has any doubts in the slides or any of the worked out examples, they can ask me in the next session, or maybe they can post it in the discussion forum also. So I will start now. Share my slides with you. Okay. So yeah, good evening everyone. So my name is good evening everyone. My name is Mayank Anupam. I am a PhD student and a PMRF scholar from the Department of Electrical Engineering at IIT Kanpur. This course is Basic Electrical Circuits, which is offered by NPTEL as part of the online MOOC courses. So it is taken by the professor of Department of Electrical Engineering IIT Kanpur, Dr. Ankush Sharma, and I am a tutor for this course. My job is to conduct tutorial sessions where you can ask your doubts, and I can solve the problems, sample problems. Okay, moving ahead. So in the last week, in week 3, you learned about different network theorems. So what were those? I'll quickly summarize them first. So in the first part of the week, you learned about the linearity property, isn't it? You learned about the linearity property and superposition theorem. So I would just like to emphasize that linearity property is a very, very, very important property in the electrical engineering domain. So not only electrical engineering, but across many domains. This particular property, linearity and superposition theorem, these two things make the life of an engineer very easy when properly used. So this is very, very important. Another thing that you learned was source transformation. So basically, we will be solving a lot of circuits as we go along the course, and this source transformation technique is a very good, I would say very nice technique to solve circuit problems, where there is you might feel that the circuits are very complicated, but then you will transform the sources and you'll see that it will become very easy, and then it will become very easy and you will be able to solve it very quickly. Another very important thing that you came across this week, the last week, was duality. So I think you must have studied in your high school physics that current and voltages, they are like dual of each other when we talk about electrodynamics and magnetics. So basically in electrostatics, in electrodynamics and magnetics, you will see that there is continuously this analogy, you can say. There is a continuous duality in electrodynamics and magnetics. So basically, okay, hold on a second. Hi Sai Shiva. So it looks like only we have joined today. Only you have joined today.
Yes.
Okay, some more people are joining. So yeah, so it's Independence Day, and people want to celebrate Independence Day. It's a national holiday, but unfortunately, we have to continue the sessions. So Anyway, I was doing the session right now, so I will be continuing with it. If you have any doubts, then you can ask me. You can interrupt me in between. You can ask me. Okay.
Okay, okay, sir. Okay.
Yeah, so is it visible? Can you confirm?
Yes.
Okay, fine. Yeah, so I was just talking about the. So let me restart. I'll just restart again. So basically, this course is basic electrical circuits, and this is taken by Dr. Ankush Sharma. He is from Department of Electrical Engineering, IIT Kanpur, and this course is taken as part of the massive open online course offered by NPTEL. I am tutor. I will be the tutor for this course. My name is Mayank Anupam. I am a PhD student and a PMRF scholar from Department of Electrical Engineering, IIT Kanpur. Okay. So last week, week 3, we learnt about a lot of, we learnt about some network theorems, right? So what were those network theorems? So sorry, yeah. So what were those network theorems? We came as the first part of the week, we learnt about linearity property and superposition theorem, right? So I just want to mention that linearity property is like the very important it is very important property in the electrical engineering domain as well as across different departments. This linearity property makes the life of an engineer very easy. Linearity and superposition. You will see that where the circuits or the problems which are non-linear are a mess to handle. So they become very difficult to handle. So there, so basically, what I want you to appreciate is that linearity property or linear circuits or linear anything linear is very easy to handle and it is very easy to solve also. So it is very important. So you should pay attention here. Another thing that you learned as you went ahead in the week was source transformation. So you will quickly see you will if you, when you solve the problems, when you solve different circuit problems, you will see that many times you will come across circuits which have like a lot of sources connected here and there, and it will become very difficult to solve them without picking up pen and paper. But it will you will see that many a times source transformation, this technique will make your life very easy and you will be able to solve the circuits quickly, uh, probably without even holding a pen or paper. Another thing that you learned was about duality. So I will touch this topic once I go ahead in the slides. So duality is also a very important point. It is not particularly important to solve circuits, but it is important to understand the duality uh, because many times uh, you will see that it is difficult to visualize certain things in the magnetic field. Basically, you know that you must have seen when you saw the videos, you must have seen that capacitor is the dual of inductor, voltage dual of current, something like that. You must have seen, isn't it? Hello. So can someone respond?
Sir, please repeat duality, sir.
Okay, okay. I will repeat. I will repeat. Yeah. So I was saying that duality is. I am sorry. Can you turn off your mic because it looks like I am hearing back my voice. So yeah, fine. So I was saying that duality is a very important theorem. Duality is very important property actually. So this is not particularly this will not be particularly helpful for solving circuits, but it is very helpful to understand duality because a lot of times you will be able to transform a circuit from transform a circuit by finding its dual, and you will see that the dual circuit which you found out is much easier to visualize. Okay, so you will be able to appreciate it much more when you move ahead in the course. So duality is not the applicability of duality, you will not be able to appreciate it just now because a lot of things have not been taught yet. But as you move ahead in the course, as you progress, you will see that this duality will come, you will come across this thing again and again. and it becomes particularly helpful when you want to visualize circuits with inductors as circuit in the form of circuits with capacitors. So I don't know about you, but inductors make me very uncomfortable. Okay, so I like to I would like ideally to get rid of all the inductors, and I would like to uh, basically visualize the inductors in terms of some capacitors and all. So that you can do when you know about duality. So that is what I wanted to just appreciate. Wanted you to appreciate. If you do not understand the use of duality now, just don't worry. It will become clear as you go on along the course. Just understand what is duality and how you can apply it. That's all. Why you should apply it or where you should apply it, that part will come later. Uh, was I clear? Was your question answered?
Yes, sir.
Yeah. So after that you came across Thevenin theorem. So Thevenin theorem also is a very very important theorem. So a lot of circuits, a lot of linear circuits. I think almost always any linear circuit you are not so okay. So I will try to explain this with an example. So suppose you have a big network like this. Okay, you have some voltage sources, some current sources, and some resistors, some capacitors here and there. So a lot of circuits. Okay, now a lot of times you are only interested in these two terminals, isn't it? Suppose you have a very complicated network here, but all you wanted was to find out the current or current like this when you connected a load RL here. Okay, suppose suppose this is your application. You are not worried about how much current is basically each and every component in this network consuming. You are not concerned about that. Let's say you are just concerned about finding the current in this particular load. Okay, and you do not want to get involved in finding all those things here. You just want to know how much current this is consuming, how much voltage across it is there. So for that particular application, Thevenin's theorem is very helpful. So in Thevenin's theorem, you just replace it with a voltage source and some resistor, which you call Thevenin resistance. This is called Thevenin voltage, and then you just connect this load here, and you say that okay, so this current will be same as here, this current. So this is basically finding out equivalent of this network. So pardon me, this capacitor will not be there. I am talking about DC network right now. Okay, so in DC network, capacitor will not exist, or even if it exists, it doesn't matter. So capacitor will anyway be not be helpful at high at steady state in DC. Yeah, so this is the condition. When you are concerned about only finding out the terminal characteristic, at that time you can replace this whole network, this whole linear network, with a Thevenin resistance and Thevenin voltage. Okay, fine. So okay, so now quickly summarizing the properties. So what was linearity? Linearity says that when you apply an input x1 to a system and you get an output y1, and you apply x2 to the system, you get a y2 output. We say that the relationship, that the x to y relationship is linear. So this point will become clear now. So I am saying that you must focus on the phrase here. I am saying x to y relationship. We say that the x to y relationship is linear if this property holds. What is this? This is homogeneity and additivity together. So basically, you scale your input x1 with some constant a1, and you scale your input x2 with some constant a2, and then you add them together and give it to the system, and then you will see that the output is also the scaled version of output to x1 and scaled version of output to x2. Both are added together. Then you will say that okay, the system is linear, and not the system but the relationship in particular is linear. Why do we say, why am I stressing on this word x to y relationship? So because you see, generally you must have heard that resistor is a linear element, isn't it?
Yes, sir.
Yes, sir.
Yeah, you must have heard that resistor is a linear element. So this resistor is a linear element. This particular this particular statement is valid only when we are talking about the voltage and current relationship. Okay, so resistor is a linear element with respect to its voltage and current relationship. Okay, so it is only linear when we are talking about the relationship between the voltage across it and the current that is flowing through it. Only then we can say that the resistor is a linear element. Because you see, the resistor has a linear IV relation, VI relationship, but has a non-linear power to current relationship. So what is power dissipated in resistor? I square R,
I square
isn't it?
R.
So you can clearly see that in this case, the relationship between current and power is not at all linear, isn't it?
Yes, yes.
Yeah. So so mind this word, because this is a point of I have seen a lot of students getting confused in the concept of linearity. They will blindly say that okay, resistor is a linear element, and whatever it is linear. So it is not the case. It is linear only when we are talking about the voltage and current relationship.
VA.
Yeah, right. So as it turns out, we are mostly generally concerned about the voltage to current relationship only. So in that scenario, yeah, resistor is a linear element. You can say loosely, but at the back of your mind, you should always be informed that it is linear only when we are talking about this voltage to current relationship. Okay. Okay. Moving ahead. Yeah. So yeah, this is a very important point which I have highlighted in red here. So a circuit which is linear, okay, this is a linear circuit or linear network. This will not have any independent source here. Okay. Basically,
Yes.
there can be no voltage or current sources here. You cannot have such things inside a linear network, because then in that scenario it will become non-linear. Because you know that a voltage source is a non-linear element, isn't it? You must have seen this. What? Okay, so what is the V2I relationship of a voltage source? Can you say?
Sir, it is straight.
Straight. What is?
Straight line, sir.
Yeah, straight line. Straight line parallel to
Pass.
what? So can you say? So I have. Suppose I am applying a voltage source of value V naught. Then what will be its VI characteristic? How will be its VI characteristic? It is a straight line. You are correct. But parallel to what? Passing through what? Straight line can be like. It can be like this. It can be like this. It can be like this. So what is a straight line? Where?
Sir, the straight line is the resistance value. The resistance value is vary when the voltage and current is vary.
No. Ideal voltage source I am talking about. So okay, maybe I was not very clear. Uh, so okay, so I'm trying
Parallel to
again.
Y-axis.
Okay. One second. So let's say you have a voltage source like this. Okay. This is one terminal. This is another terminal. This is the current that is flowing through it, and this is the voltage which is across it. Now I am saying, and let's say this voltage source value is V naught. Okay. Now I am saying, tell me what is the VI relationship? How will be the voltage and current? How will the voltage vary when you vary current across it? So basically, if you change this current, how will the voltage across these two terminals A and B vary? That is basically what is VI relationship, isn't it? So
Yes, sir.
can you say what will be the curve look like? How will be the graph?
Parallel to Y.
Parallel to? Yeah, go ahead. You are right. Parallel to what?
I-axis.
Yeah,
Current axis.
correct. And what will be this value? What will be this value? This will be V naught, isn't it? So what this graph says is that it doesn't matter how much current you are taking out of the system. So how much current is flowing through it, it doesn't matter. It will always maintain a voltage V naught across terminal A and B, isn't it? So that is why this voltage is always constant. The terminal voltage V across AB is always constant and is equal to V naught. It doesn't matter how much current is flowing through it, isn't it?
sir.
Yeah. Now what is
Sir,
the
the voltage is always constant or with I.
yes, it is the characteristic of an ideal voltage source.
Yes, sir.
It is the characteristic of an ideal voltage source. It will always be constant. It doesn't matter how much current is being pulled out of it. Now, if you want to find out the voltage to current relationship of a resistor, now this is V, this is I. What will it look like? So take this resistor for example. Okay. Now a current I is flowing through it, and this is the voltage across it. So how will be this characteristic? How will this characteristic look like?
Straight line passing through origin.
Correct. Straight line passing through origin, isn't it? And what will be this slope?
V by
What will
R.
be this slope? It will be R, right?
R.
It is slope is V by I, isn't it? Its slope is V by I, and it is always equal to R. Ohm's law, isn't it?
Yes, sir.
Yeah. So you see that in this case, when you change the current across the current through the resistor, the voltage across it is also changing in some fashion, right? And it is passing through the origin. So this is a linear relationship, voltage to current relationship here. It is linear. But here what is this? If you change the voltage, if you change the current flowing through the voltage source, nothing will change in the voltage. So voltage will not change across it. So basically you cannot apply this superposition theorem here for a voltage source. So I said that what was that? If your input changes, your output changes, and when you sum both of these, you will see that the output is also a sum of both of these. But for a voltage source, when you suppose I1 voltage, when a current I1 is flowing through a voltage source and voltage across it is V0. Now suppose I am changing the current to I2, but still the voltage through it will be, voltage across it will be what? V0 only, isn't it? For a voltage source, this will be V0 only. It doesn't matter how much current is flowing through it, right?
Yes.
So when current I1 is flowing, the voltage is V0. When current I2 is flowing, voltage is again V0. So basically you see that there is a clear conflict here, right?
Yes.
So this superposition will not be holding here. So that is why a voltage source is a non-linear element. So that is why in any linear circuit, there is no provision. You cannot have any voltage source or any current source.
Current.
Okay. So that is why I have highlighted this point here. Okay. Fine. So there is no doubt till here, right?
Excuse me, sir.
Yeah. So there is no doubt.
Sir, within the linear system, any dependent network.
Yeah, dependent can be there. There can be dependent sources here. There can be dependent sources here, but there cannot be any independent source here.
Okay, sir.
Okay.
Okay.
Any other doubt?
No, sir.
Okay, fine. Okay, then we also talked about superposition. So what is so basically superposition is helpful whenever a circuit has two or more independent sources. In that case, you can apply superposition theorem to find the voltage and current in the circuit. Okay. So basically, what does it say? It says that superposition. It says that the voltage across or current through an element in a linear circuit is an algebraic sum of the voltages across or current through that element due to each independent source acting alone. Right. So this was anyway covered in the week. So any doubt here in this statement? Any doubt? Okay, so this will become clear as we solve a question today. So I will be solving a problem. It will become clear. Okay. Yeah. So when you are applying superposition, you have to be careful that okay, at this point, this red point I will be covering in the next example. Okay. So this is the example. So I will be solving this example now. So okay. One second. Yeah, is it visible? My screen?
Yes, sir.
Yeah. So okay. So now let us look at this problem. So here we have to find the voltage across this 4 ohm resistance, right? So there is how will you do this? How will you solve this problem? How will you go ahead and solve this problem?
Nodal. No.
Okay, so you will do nodal analysis, right? So let's say this is voltage V1, this is V2, and let's say this is reference. Then you will write some equations and you will try to find the uh, voltage and current across it, right? Right?
Yes, sir.
Yeah.
Yes, sir.
Fine. So now let us proceed. Let us try to solve this problem in a slightly different manner by using superposition. So what superposition says is that, so you see there are three sources here. This is current source, this is voltage source, this is also a voltage source. Now what superposition was saying that is that the voltage across this particular terminal, the voltage that we are concerned here, that is equal to the algebraic sum of the voltages that each and every one of these sources will enforce on this particular resistor, across this particular resistor, without the effect of any other source at a time. So what does that mean is that for we will what we will do is that we will find out the voltage across this 4 ohm resistor due individually due to 14 volt, due to 1 volt, and due to 4 ampere current source. We will find out the voltage individually because of all of these sources, and then we will add them algebraically. Okay, so this will become clear as I do it. So let's say first what I will do is that I will find out the voltage due to V naught due to what, to 1 volt. Okay, 1 volt source. So what do you do is, in that case, you short 14 volt and open 4 ampere
4 amps.
current source, right?
Yes.
Yeah. So if you have any doubt, then you just stop me and you ask that doubt. Okay. So now how will my circuit look? This is 6 ohms. Uh, this is 3 ohms. Then there is this 6 ohms again. Then there is 14 volt is shorted, so that is gone. And there is 8 ohms. Then there is this 4 ohm. Then there is this voltage source. Right? Yeah. And then there is this reference. Right? Now what is the voltage across this? This is the voltage that we are interested, right? V naught. Across terminal A and B. Sorry, B. So what will be the voltage for that you do this? First you find out the parallel of these. So what will be the equivalent resistance here? This will be equal to 6 into 3 divided by 6 plus 3 becomes 2, right? 2 ohms. So now the circuit will transform to what? Circuit will transform to this 2 ohms. Then there is this 6 ohms. Then there is this 8 ohms. There is 4, and then there is this voltage. And this basically this reference. Now again you do this 8 ohm, this 2 and 6 are in series. So effectively it becomes 8 ohm. And this 8 and 8 are in parallel to each other. So effectively they become what? 4 ohms. So this is 4 ohms. This is again 4 ohms. And there is a voltage source here. V is equal to 1 volt. Right? Now you want to find the voltage across this A and B. What will be the voltage across this? Tell me, what is the voltage across it? Hello? Uh, Sorry, there was a problem at my end. Am I audible?
Yes, sir.
Okay. I'm really sorry. There was a problem at my end, so my computer suddenly switched off. I'm very very sorry for that. I'll again share the screen now. Okay, so I was at this point. Yeah, so till this everything was clear, right? So you were able to hear me till this point.
Yes, sir.
Okay. So now tell me what is this VAB in this case? Hello.
1/2, sir.
1/2.
Equivalent resistance.
Right. Equivalent resistance
Yeah,
is what?
8 ohm.
Right. You're correct. It is 1/2. But I'm asking about the voltage VA minus VB.
4 series.
Yeah, you are true. It is 1/2 volt. Right. True. But it will not be. You are telling the magnitude. I'm also asking the sign. So it is not 1/2. It is minus 1/2. Right.
Sir, I'm not clear.
Okay, fine. So I will explain this point again. So okay, so this circuit can be rewritten in this form, right? Plus minus. There is a voltage. Uh, I'm sorry. There is today something is happening with my computer. I'm really sorry. Am I audible and visible now?
Sir.
I am really sorry about it. I don't know what is happening today. Generally, it doesn't happen like this. Okay, but 1 second. I will be sharing again. Yeah. Okay. So I was telling about this. Yeah. So this is the situation. This is 1 volt, isn't it? Now there is a resistance of 4 ohm here, and there is another resistance 4 ohm here. Now this is A and this is this is B, and now I am asking you VAB, which is equal to VA minus VB, right? So now
Yes, sir.
now can you say what is the voltage VA minus VB? So you were true that the voltage across it will be half volts. That is true, but I am asking about VA minus VB. So basically, can you understand? Can you when I say, if I say that this voltage here will be higher than this voltage here, are you satisfied with this statement?
Yes,
Is
sir.
this statement true? that VB, this voltage, is higher than this voltage?
Yes, sir. Yes.
Right. Now,
Yes.
you were also right when you said that the voltage across this 4 ohm resistance is 1 by 2 volt. That is true. But I'm asking about VA minus VB, this minus this. And you just agreed that VB is greater than VA. So definitely that voltage that I'm asking you about, this VA minus VB, should hello, hello. Yeah. I don't think it should turn off now. Fine. Yeah, so I was sharing something. Okay. So, is it visible?
Yes, sir.
Okay. So I was saying that. Yeah. So you just agreed that this voltage VB is greater than VA, right? So I'm asking
Yes.
about VA minus VB. So that should definitely be less than 0, right? That should be negative. Am I right? Hello.
Yes, sir.
So definitely in that case, you can say that the voltage VA minus VB will be what? It will be minus. Okay, something is happening here. Voltage VA minus VB will be what? It will be VA minus VB will be equal to minus 1 by 2
Minus 1.
volts, right?
Yes.
Okay. Okay, fine. Now that we are clear here about it. So due to uh, due to 1 volt, you got V naught is equal to minus 1 by 2 volts. Now you need to find out. Let's try to find out what due to 14 volts. Okay. So how will be the circuit look how will the circuit look like in that case? Due to 14 volts. So let me drag it down here so that it becomes easier for you to visualize. You see, yeah. So what will the circuit look like when you want to find out due to 14 volt? You have to open 4 ohms, 4 amperes. This is 6 ohms. Then there is this 3 ohms. This is like this. Then there is the 6 ohms again. Then there is 14 volts here. Then there is 8 ohms here. And here is 4 ohms. And this is shorted here. And you need to find out this voltage again, right? And this is the reference. Okay. Fine. Now again here, this 6 and 3 in parallel will become what? They will become 2 ohms. 2 plus 6 in series will become 8 ohms, right? This in series will become 8 ohms. So my net circuit again will become like what? So it will be 8 ohms here, 14 volts here, then again this 8 ohms here, and then there is this 4 ohms, and then there is this reference here, right? Hello? Yeah. So now what should I do? Can you suggest something? Now what should I do? I need to find out this voltage. So what should I do now? Okay.
Sir,
Yeah.
we done the source conversation 4 volt and 8 ohm.
We can do that, but I don't want to touch source basically conversion here. I can definitely do that. You're right. You can do source transformation here. But suppose I don't want to do source transformation. I just want to do it in the normal conventional way. So what should I do now? So you can see that this 4 ohms and this 8 ohms are in parallel, isn't it?
Yes, sir.
Right. So
Yes, sir.
what will that become? So 4 ohm is in parallel with 8 ohms. So this becomes 4 into 8 divided by 4 plus 8. This becomes 32 by 12. Right? Right? This becomes how much? 4 8s are 32, 4 3s are 12. 8 by 3 ohms. Now what we have? Equivalent. Now we have a voltage source like this, 14 volts, and then we have a resistance like this, 8 ohms, and then we have a resistance like this, which is 8 by 3 ohms. And I am telling you to find the voltage across 8 V naught. So basically this 4 volt and 8 4 ohm and 8 ohm equivalent resistance will be again parallel to all of this, right? So
Yes, sir.
voltage across 8 by 3 is same as voltage across 8 and voltage across
8 ohm.
right?
Okay, okay, sir.
So what will be the voltage here? V naught.
As per voltage division,
As per voltage
40,
division, what will be the voltage?
40 meter.
Yeah, say something. But what do you think here should I? So voltage division, how will I apply here? So VAB should be equal to what? 14 volts multiplied by
Two.
8 by 3 ohms divided by 8 plus 8 by 3, right?
Yes.
So what does this voltage division rule say? If you want to find the voltage across a particular resistor R1, then what you have to do? You have to multiply that. You have to basically say that. You have to basically do what? You have to if you want to find out the voltage here, then the voltage is given by what? V times this particular resistance divided by the total resistance that you are seeing, right?
Yes.
This 2 in series, so 8 plus 8 by 3. This is how much? 14 volt multiplied by 8 by 3 divided by how much? 32 by 3, right?
Yes, sir.
So this becomes 32 by 3. 3 and 3 are gone, so this becomes 14 volt. 14 multiplied by 8 by 32, which becomes 14 into 1 by 4. How much is this? 3.5, right?
Yes.
So this is plus 3.5 volt. So V naught due to 14 volt is equal to 3.5 volts plus 3.5 volts. Okay. Now the final one. Now we have to find out the voltage due to this 4 ampere current source, isn't it?
Yes.
So now let us do that. Now the third one is V naught due to 4 ampere current source. Hold on a second. There's someone wants to join. So let me join that. Okay. Sorry. One second. Okay, so this is visible, right? Hello.
Yes, sir. Visible.
Okay.
Fine.
So how will the circuit look like when I want to find out the equivalent for 4 ampere? So I have to keep the 4 ampere current like this, and then I have 6 ohms here. Then there is this 3 ohms here. Then there is 6 ohms here.
Okay.
Then there is 8 ohms here. Then there is 4 ohms here. Let's call this one as the reference node. Right. Now what is the voltage here?
So we want to find
VA minus VB is equal to V naught, right? So how will you do that? What should you do now? Tell me. Come on, people, say something. Otherwise, it will feel like so you are not understanding anything. So am I not clear? So I understand that today there has been some problems with my computer, but other than that, whatever I have told till now, is it understood? Is it clear to you? So what I am doing right now.
Yes, sir.
So if something is not clear, then tell me. Stop me, interrupt me, and then ask me those questions. Because that is why these sessions are held. If you don't ask me questions, if you do not understand these things, then it's just worthless, these sessions. Okay, so what should I do? Tell me. What should I do? How should I find out the voltage here? What should I do?
So 6 3 are parallel.
Correct. 6 3 are in parallel, so this becomes how much? 2 ohms?
This is 2 ohm. And 2 and 6 are series.
Correct. So what will that become?
So this is 8 ohm.
Correct.
And 8 ohm is also parallel.
Correct.
This is 4 ohm.
Correct. Very good. This becomes 4 ohms. So and what?
This 4. So then we.
Yeah, right. Again, so how will the circuit look like? So this become very complicated. So this is 4 ampere, then there is a 4 ohm here, then there is again a 4 ohm here, right?
Yes, sir.
Now you want to find this voltage V naught. So now what you should do? Yeah, so you till now you were very right and very good for that. So now tell me what should I do? Now we are at the final stage. It is very easy now. Tell me what should I do now?
Current division.
You can do current division, but why should you do current division? Yeah, you can do current division, true. So how will the current? How much current will be there here and here? Tell me.
Same current.
Same current. Why? This 4 ampere current is flowing in this branch. So there are two branches here. So don't you think that it will try to divide itself within these two branches? here and here.
Yes,
So
sir. 2 ohms.
correct, 2 amperes.
2
Right?
amp.
Correct. Now tell me what is the voltage here? If it is 2 amperes in both the branches, what is the voltage here? 2 amperes is flowing through a 4 ohm resistor. So how much voltage should be there across this resistor?
So 8 volts, sir.
8 volts.
Correct. Very good. And what will be the sign of this 8 volt? Plus or minus? So did I show this?
Sir, reverse, sir. Reverse.
What? Reverse.
Sir, yes,
Minus.
sir. So plus is plus
Correct. So basically, okay, I understood. You see this 4 ampere, this is flowing like this, right? So in this branch the current is like this. So here I showed the current to be like this. So am I showing it correctly or wrong? There is something wrong here.
sir, correct, sir.
Wrong.
No, it is wrong. Because you see the current is being pulled out of these branch here. You see the current is being pulled out here, right? It is being pulled out
Yes,
here. So current here should be how? It should go up like this. Not, it should not flow down. It should go up. So now can you tell me what is the voltage V? VA minus VB. I said that this current 2 ampere is flowing and it is flowing in this direction. Now tell me what is VA minus VB?
Sir, plus 8 volt.
No, it should be minus 8 volt. Because you have this, this is VA, this is VB. You have current flowing like this. 2 ampere across 4 ohms resistor. So this becomes VA minus VB is equal to how much? 4 into minus 2, which becomes minus 8 volts. If the current is flowing like this, then it is true. Then it becomes 8 volts. But the current is flowing in the other direction.
Yes, sir.
VB to VA, the current is flowing VB to VA, isn't it? So the drop should occur where? From VB to VA, the drop should occur, not the other way around. So that is why when you say VA minus VB, it will become minus 8 volts. Correct?
Yes, sir.
Right. So now that we have done this, now tell me what is the total voltage. So what we did here, we okay, hold on. So let me write it here. V naught due to 4 ampere current source is equal to minus 8 volts. V naught due to 1 volt voltage source. How much was it? It was, you see, minus half volt, right? It was minus half volt. So you see we have done this here. So it was minus half volt, right? Okay.
Yes.
So due to 1 volt voltage source, the voltage was minus 0.5 volt. Now there was another voltage source, 14 volt, right? So we have done it here. Due to 14 volt, there was plus 3.5 voltage, right? So let me write that here again. So V naught due to 14 volt voltage source is equal to how much? Plus 3.5 volts. So total voltage will be how much? According to superposition. Tell me. What was superposition?
Minus 5.
How much? So what you should do now? Tell me. If you want to find the total voltage there, you have found out the voltage for all the individual independent sources. Now I want to find the total voltage at that actual voltage basically at V0. I have found out V0 due to all the individual sources. So what does superposition say?
Sum of all the
Sum of
Correct.
all
individuals.
Sum
these.
of all these.
And what kind of sum? Algebraic sum.
Algebraic.
So you can take the sum in the form of magnitude also. That is not true. You have to take them their signs also. You have to sum them with their signs. So it will be minus 8 plus minus
Minus
0.5 plus 3.5 volts. Isn't it? And how much will be this? Right?
minus 5.
Correct. Minus 5. Is it right now?
Yes.
Okay. Hmm. Right. So this answer here is wrong, isn't it? So this was just to make sure that you guys follow with me. Otherwise, someone can just. Uh, so I have. Okay, so you are not able to see this. 1 second. Yeah. So how much is the voltage? 5 volts. Minus 5 volt, right?
Right.
Yeah. Okay. So do you have any other classes now?
Yes, sir.
Yes, sir.
Okay. Okay, fine. So,
Sir, one question, sir.
ask me.
Sir, in Vm sin omega t, there omega t is what, sir?
Yeah, that is called the
Right.
phase. Omega t.
Sir, there is omega is what, sir? Frequency or?
Yeah, it's angular frequency. It's not
Yes,
the
sir.
typical frequency that you heard about. It is angular frequency.
Yes, sir.
Its unit is
Sir,
radian per second.
yes, sir. Sir, if we say multiply the sinusoidal wave and the square wave, the triangular wave, then the answer is what, sir?
I couldn't hear you. Can you just repeat your question?
Sir, if we multiply the triangular wave and the sine wave, then the multiplication is what, sir?
If you multiply the sinusoidal with a triangular wave,
Yes, sir. Yes, sir.
then what is the multiplication?
Yes, sir.
So that you do it now. So multiplies directly. I am not able to prove your question. So you can post this question on discussion forum. So I will look at it.
Yes,
Because
sir.
I'm not able to understand your question right now.
Yes, sir.
Yes, sir. Okay, so fine. If you have any other classes, then you can go.
Yes.
We will continue it next time. Because I had other
Thank you, sir.
classes, so I could not unfortunately do it. I'll do it next time. Okay?
Yes, sir. Thank you, sir.